Now that we know how to work with radians, we're going to look at an application and look at linear and angular speed. There's some formulas that we're going to want to work with here, and both of these formulas are going to be based on a formula we already know called distance equals rate times time. So for instance, how far would you travel if you were going 60 miles per hour for 3 hours? Well, the hours would cancel here and I'd be left with 60 times 3 is 180 miles. So this is an application of just our distance equals rate times time type of formula. And what we're going to do is we're going to turn this into something a little bit different. So distance equals rate times time. Rate is also known as the speed. And of course time is self-explanatory. You always need to make a look at the problem and make sure that you're using minutes or seconds, because sometimes it'll give you information in terms of minutes and another piece in seconds, and you have to make sure that you convert everything properly. Distance then, if we were trying to relate this to what we're usually working with, would be something like arc length. So speed, another name for speed, would be velocity. So if we were to take this formula, we would have arc length, and so we could call arc length S equals speed, which would be velocity, times time. Now if we solve this for velocity, I divide both sides through by t, and I get velocity equals S over t. So again, v is velocity, s is arc length, t is time. So this is an important formula to know, and this is the formula that we use when we're trying to track linear speed. Now this formula is good for a lot of other things other than just v equals s over t. For instance, I could look at this same formula and I could solve it for t, or I could solve it for s. So it kind of depends on what information you're provided and what you're being asked for. Now there's another formula that we can also work with, and it's called angular speed. Now what we use to represent angular speed is, looks like the letter W, a lowercase w, but it's pronounced omega. It's a Greek letter omega, and it has kind of this curve in. And so that's kind of how I distinguish it. And you can see when we get into your textbook or when you look at the My Math Lab problems that it looks printed a lot better than it does written. So we have this formula for angular speed. So again, velocity and this angular speed are related. S is arc length, but we don't care about arc length now. Now we care about theta, how theta is changing at some particular time t. So W, or omega, in radians per unit of time t, and theta is in radians. So theta is in radians, just like it was for arc length and area of a sector. Now a lot of interesting things can happen here. So for linear speed, I could think about this v equals s over t, and arc length we know is r times theta over t. So this is from the fact that s equal r theta from our previous information. So if we look at this v and we look at theta over t times r, theta over t we know from up here is omega, so I get v equals omega times t. And this would just depend on what information is given. So this might be a quicker formula to use, is if we have velocity would be our our angular speed times the amount of time. So there's another formula that we could use for that. And of course we also looked at another one down here before we got to that, and that was r theta over t. And of course r is radius, theta would be the angle in terms of radians, and t is time. So important things to remember here are these two right here, linear speed and angular speed. Once you know these, you can come up with these other two that I have listed here, but it might be a good idea to have them on a note card to help you refer back to them. From here we're just going to work a lot of problems, because these can be a little bit tricky until you get used to them. So for our first problem, let's go ahead and pick one from My Math Lab. So let's look to see what we have for our first problem here. It'll be important to make sure we can summarize our information. Here we have r equal 14, so that's the radius equals 14 centimeters. W, or this omega is the correct way to say that, is angular speed. And of course our t equals 4 seconds is kind of self-explanatory. So what ends up happening here is we have some point P that's traveling around a circle, and we're looking at angular speed for this, and they want us to find each of these given values. So for our part A, it says what angle is generated by P in time t. Well, if we think about this, if I want to know how much angle or what the size of the angle generated is, I could look at this in terms of how far the angle is moving. So it's moving radians per second, and it's moving for a certain amount of time. So with those two pieces of information, I should be able to come up with the angle being generated. So let's look at one of our formulas. We know that we're talking about angles being generated. We're given omega right here. So one formula that we could maybe start with is omega equal theta over t. So this would be the angle being generated. Now if we want to solve this for theta, I could multiply both sides through by t, and I get theta equals omega t. So theta is the angle being generated. Omega is pi over 6 radians per second. And time then would be 4 seconds. And I'm going to write this as 4 seconds over 1 just so we keep our numerators and denominators straight. So you'll see here that seconds cancel, and I'm left with 4 pi over 6 radians. So theta equals reduced 2 pi over 3 radians. This would be the angle being generated. This is the angle generated. So sometimes you have to look at the information that's provided in order to choose exactly the correct formula that we can use here. Okay, for part B, we might use this information, and we might have to go back to what we were given. It says, what is the distance traveled by P along the circle? Well, this would be a formula for linear speed, perhaps, when we're looking for distance, which seems like it would be arc length. So let's think about this in terms of arc length. So distance traveled would be arc length. Okay, so we have a little bit of information there. We know the formula for arc length is S equal R theta. So if we go back and have a look at our formulas that were given, we should be able to look at R as 14, it's given to us right here. And then theta that we just found was 2 pi over 3. So let's go ahead and plug that in next. So S is equal to R, and again R was provided to us. I want to make sure I get the correct value, 14. And theta we just found would be 2 pi over 3. So if we multiply those, we'd end up with arc length 28 pi over 3. And that is the distance traveled by the point along the circle in 3 seconds. So that's part B. Let's go ahead and look at the third part that they're asking us about. Now for this third part, they're actually asking for the linear speed of the point. So they've broken this down really nicely for us, kind of a step-by-step process. So we should just be able to look at a formula for the linear speed of P. So our formula for linear speed would be v for velocity equals s over t. Well, we know s in this particular case is 28 pi over 3 and then divided by t. So t in this particular case is, did they give us to that up top? 4 seconds. So 4 seconds was given to us up top, 4 seconds. Okay, so if we kind of come back up to this part B, distance traveled, I should have some units on that, and it should have been centimeters, because that's what we were given. So this would have been centimeters. So now when I'm working through this problem, this is going to be centimeters here. And when I'm looking at our arc length in this comparison, remember when you divide by a fraction, you're multiplying by the reciprocal. So this would be 28 pi over 3 centimeters times 1 over 4 seconds. When you divide by a fraction, you multiply by the reciprocal. So that's an important thing to keep in mind. Now let's see how our units come out here. If we cancel, it looks like 4 will go into 28. So 4 cancels into 28, 7, so I'm left with 7 pi. I have 7 pi centimeters per 3 seconds. So 7 pi over 3 centimeters per second. So our solution here would be, what is the linear speed? Meters per second, miles per hour. This one happens to be centimeters per second. So again, when they break it down for you like that, these are a lot easier to work with, but we're using those same formulas over and over again. And speaking of using the same formulas, let's go ahead and look at a problem where we're given the formula to work with and then just asked to plug in and solve for a different variable. So we're going to use the formula for angular velocity, or angular speed. It means the same thing. And find the missing value. So let's figure out first what we know, and then what we don't know, and then what we need to find that's missing. So the formula for angular speed, because they give us angular speed right here, is omega equals theta over t. So if we plug in here, we give omega is 5 pi over 8 equals theta, I don't see anything for theta, and then t is 32. So we have a couple things that we could do here. To clear this fraction, we could multiply both sides by 32, or you could also cross multiply. It's kind of what your preference would be. Now remember, this is really 32 over 1, so 8 goes into 32. 8 times 4 is 32. So on the left hand side, we have 4 times 5 pi equals theta, because these canceled. So I'm left with theta equals 20 pi. So that would be my answer here. So this one I was able to solve for theta, but it really depends on the problem that you're given, because you could have been asked to solve for t or omega depending on what information was provided. Let's look at a one that's similar to that, and let's see if we're given different information and if we can solve for the other variable. Okay, so for this one we're still using that same formula. Omega equal theta over t. But our given information here is different. Here we don't know omega. We do know theta, 3 pi over 5, and t is 8 seconds. So we need to figure out how to work with these fractions. So again, when you divide by a fraction, you multiply by the reciprocal. So this is actually equal to 3 pi over 5 divided by 8. And I want to write 8 over 1. When you divide by a fraction, you multiply by the reciprocal, so this will flip. So I will be left with 3 pi over 40. Now if we were keeping track of our units, which I probably should have been, this would be radians per second. So radians per second. So 3 pi over 40 radians per second. So again, it depends on what information is provided. You can use that formula for a lot of different things based on what's provided versus what you want to be finding. Let's look at one more, just so we get used to solving for different variables. Kind of some algebra review there. Okay, so they give us another formula here. They give us V equals R omega. So here, I don't see that we have a V. We are given an R is 20 meters. And omega is 3 pi over 4 radians per second. Okay, so I'm kind of curious what's going to happen with our units on this one. So let's double check those. So the 3 pi over 4, radians per second. Remember, radians isn't a unit of measure like inches or feet or meters, so we really don't even need to include it. So we should be left with meters per second when we're done. If we want to, we could write this as 20 over 1. 4 goes into 25 times. So I'm left with 5 times 3 pi meters per second. So 5 times 3 is 15 pi meters per second. And if you wanted to kind of throw in a radian or something here, remember it's already in here because 3 pi over 4 was the measurement that we were looking for in terms of radians. Okay, so I think we've looked at quite a few different types of those problems where we can solve for different variables. In our next one, we actually want to look at an application problem. Now with the application problems, we need to read these carefully, and we also need to really keep track of what is being provided and what we're being asked to find. So this one we're going to be working with a 75 horsepower outboard motor, it looks like. So here we have a 75 horsepower outboard motor at full throttle, and they tell us at full throttle that it will rotate the propeller exactly 4,800 revolutions per minute. So this 4,800 revolutions per minute, that's providing us with some information. So in 1 minute, the propeller makes 4,800 revolutions per minute. Now we're going to do something with this information. I'm just trying to break down what's being provided to us so far. So each revolution is a full spin. So if you think about it, a revolution means going in a circle, and a full spin around the unit circle is 2 pi radians. So each revolution is 2 pi radians. So each revolution is 2 pi radians. So 4,800 revolutions per minute. What I could do is think about 1 revolution in the denominator, unit, we're trying to cancel units here, times 2 pi radians. And if we simplify this, then we get 4,800 times 2 pi, revolutions cancel, and I'm left with radians per minute. So 4,800 times 2 would be 9,600 pi radians per minute. Okay, so that's some information. Now remember, we're trying to find the angular speed. Now the formula for angular speed, we are going to have to kind of look back and see what variables we want, but basically angular speed is going to be, let's go ahead and scroll back up, omega equal theta over t. So that's this one right here. So omega equal theta over t. But we might need to use a different form of that. So let's look to see what we have. So this one I don't think that formula is going to help, but this will help us up here. Find the angular speed of the propeller in radians per second. So we already have radians per minute here. So let's take that radians per minute, 9,600 pi radians in 1 minute. And we want radians per second. So we're already looking at that angular speed when we multiplied by this 2 pi when we were talking about the revolutions. So we can convert here. 1 minute is 60 seconds. So I want to make sure that the minutes will cancel, so minutes go on top. And I'm left with radians per second now. So this would equal 9,600 pi over 60 radians per second. Now one thing I want you to keep in mind is this will have to be simplified as per the instructions. So they might say reduce this fraction, or they might say round this and get a decimal approximation to the nearest tenth. So you'll just have to make sure you read the instructions for each individual problem. If this was an exact form, 9,600 divided by 60 would be 160 pi radians per second. Okay, now if we didn't want the exact form, we could also go ahead and simplify this. So this is exact form, and then to find the decimal approximation, if they want us to round that, we could just plug that into a calculator. 160 times pi is 502.6548. 246. Now if they ask us to round this to, let's say, the nearest tenth, here's the nearest tenth, so this value of 5 is 5 or above, so I would round this to a 7. So this would equal to 502.7 radians per second. And this would be the rounded solution to the nearest tenth. So again, it's important you just read the instructions. You can either give an exact solution or a rounded solution depending on what they're requesting. So for this next one, we're given an orbit type of problem. So we have this planet XYZ, and what it's doing is it's orbiting around the star in the middle. If you want to think about that as the origin, you can, ABC. And it's a circular orbit, and it takes 24 hours to make the orbit. It says assume that the orbit is a circle with radius 76 million miles. It says find the linear speed. So we're looking for linear speed in miles per hour. Okay, so let's go ahead and summarize what we have here and then see if we can solve this problem. So we have one orbit, and one orbit happens in 24 hours. So in 24 hours then, we know that we've gone clear around the circle one time, so that's 2 pi radians. Okay, so there's some useful information. I'm also given that radius, the radius of the distance from the ABC center to the XYZ planet is 76 million miles. Now remember, we want our final answer in miles per hour. So if we want to look at the linear speed, let's go ahead and look at the equation for that. Linear speed is equal to the arc length over time. So in terms of variables, that was linear speed equals arc length, which is s over t. So arc length we know is r times theta, and of course time, we'll just use that variable t. So arc length is r times theta. R is the radius. So the radius for this problem is 76 million. Theta, we're going to have to think about theta. It went clear around the unit circle, it went clear around the circle, not the unit circle. So that means it rotated 2 pi radians, and that always has to be in terms of radians. And t would be time. Now in this particular case, it says 24 hours to make an orbit. So I would be dividing this, all of this is happening in 24 hours. Now remember, this is miles, so I'll keep that in mind too. So for my linear speed, which is v, I'm going to have 76 million times 2 pi over 24 hours. So this is miles per hour. So sometimes they're going to want these answers a little bit different. Sometimes they'll want them rounded. If you want to do some simplifying and canceling, you can. But if you just want to find the decimal approximation, you can just plug it into your calculator. So when I plug this into my calculator, I get 19,896,753.47. So if they wanted us to round this to the nearest integer or the nearest mile per hour, our linear speed, if they asked us to round it, so you have to read the problem, is 19,896,753 miles per hour. Now, I rounded this to the nearest integer, so this 4 does not increase the 3. It's not 5 or larger, so I would just keep it as a 3. So there's an example where we're trying to look at a problem and make sure we do the correct conversions, and keeping track of units is really helpful. I'm sure you all have done plenty of unit conversion, and keeping track of those units and seeing that centimeters cancel or meters cancel is very, very helpful. Let's go ahead and look at another one. This problem talks about the movement of the second hand of a clock. Actually, it's the minute hand, so we'll be careful that we make sure it's the minute hand. So if we think about the minute hand of a clock, in 60 minutes, it goes a full spin around the clock face. And the clock face is a circle. So let's go ahead and write some summary information. The clock hand is 4 centimeters long. Okay, so that's some information. So in 1 hour, which is 60 minutes, there's one full rotation of that minute hand. So there's one full rotation. One full rotation around a circle is 2 pi radians. So the full rotation translates to 2 pi radians. So that's going to be interesting. Now it says find the velocity of the tip of the minute hand of a clock. So velocity. So let's go ahead and write our formula for velocity. Velocity is equal to arc length over time. So arc length, if you recall, is r times theta over time. R in this case is 4 centimeters, that was given to us up here. Theta we could figure out because it was only one full rotation, so that's 2 pi. And then our time, so we have 4 centimeters, 2 pi. The tip of the minute hand went around in 60 minutes. So our time would be 60 minutes. So 4 times 2 is 8 pi. R theta, yep. So our multiplying straight across here, and end up with 8 pi over 60. And this is centimeters per minute. Reducing, I would have 4 pi over 15 centimeters per minute. Okay, so that gives us the velocity of the tip, not the angular velocity, but the velocity of the tip there. Sometimes pictures help with these, but because like the angle is changing, the vertical angle in the center, and because it's also changing on the outside, it's hard to draw that picture because things are changing and we always have to keep track of those changes, and the pictures can get a little bit cluttered. So relying on formulas here is sometimes a little bit better. Let's go ahead and look at another example. Okay, so we're looking at linear speed here. It says the point on the edge of a flywheel, and the flywheel has a radius of 16 centimeters. So that's some important information. So radius is 16 centimeters. It's rotating at a rate of 13 radians per second. Okay, so 13 radians per second is some important information for us. So that's giving us theta over t basically. It's telling us the amount of rotation and the amount of time. So let's go ahead and see how we can write that. So we know our formula for linear speed, it's right here, is velocity. Velocity is equal to s over t. S is arc length. So this is given by r theta over t. So V equal r theta over t. R in this case is 16 centimeters. Theta in this case, they give us this. They say 13 radians per second. So this would be 13 radians in 1 second. So this would give us an idea of what our linear speed is. And of course t is time. That's this 1 second. So 13 radians in 1 second. So this whole thing is really our angular speed, radians per second. So if we want to figure out what's going on in centimeters per minute, I need to do our unit conversion, and in 60 seconds I have 1 minute. So let's go ahead and look at that velocity again. I have seconds canceling, so make sure we have everything canceling correctly. And again, radians are not really a unit of measure. It just help me keep track of the revolutions, so I can kind of just ignore that. So I'm going to have 16 times 60 in my numerator. So I have 16 times 60, and then in the denominator I have minutes. So let's go ahead and write this out. I have 16, I have 13 as well. 16 times 13 times 60 centimeters per 1 minute. So if I multiply this, 16 times 13 times 60, I have 12,480. So I have 12,480 centimeters per second. Or wait, per minute. Remember, we converted, so I have to keep that in mind. So 12,480 centimeters per minute. So again, these problems are a little bit long, but they're very doable if you break them down and apply the formulas correctly. Let's go ahead and look at another one where we're looking at an orbiting planet. But this one is a little bit different. So start a new page. So we have a planet XYZ, and it's traveling around a star. So that information is given to us, and let's pop in a picture. Okay. Assume the orbit is a circle and the radius is 86 million miles. So radius is equal to 86 million miles. Okay, so that comes from right here. And assumes there are 24 hours in one day on the planet. So one day equals 24 hours. So we're used to that. Now, as we look through this problem for part A, though, things are changing a little bit. For part A, it says assume that the planet year is 388 days. So let's look to see how that's going to change. So for part A, we need to look at 1 year equals 388 days. Okay. So as we try and answer this question for part A, it says assume that XYZ planet year is 388 days. Find the angle formed by XYZ's movement in 1 day. So we're taking the total amount of rotation here and we're splitting it up into 1 day increments. So a full orbit is going to be 2 pi radians around. So this would be 2 pi, and then I have a year of 388 days. So this would be, if I reduce this then, 388 divided by 2 would be pi over 194. So pi over 194 would be the angle formed by this movement in 1 day. So this is an angle. And we could call that angle theta from up here. So that's part A. Let's go ahead and look at part B. Part B says, give the angular speed in radians per hour. So we're looking for angular speed in radians per hour. So we better find that angular speed formula. So the formula for angular speed was omega equal theta over t. Okay, so we know something about theta. We just found that in part A. So that was pi over 194. Now if we wanted to put some units to this, that would be radians per day. Now t is our time, so this is what happens in 1 day. Okay, now usually I just think about this day as being in that denominator. Now we want to figure out what's happening in radians per hour. So in 1 day, I have to think about how many hours that I have going on. So in one day, for this particular planet, it says that it is 24 hours in one day. So I could just take one day is equal to 24 hours. Okay, so multiplying, I have pi over 194, and then I'm going to have, this is going to be multiplied by 24, but I'll give you some more detail on that, how that works. So pi over 194, and again this is radians per day, times 1 day is 24 hours. So when I simplify this, I'm going to get my angular speed is equal to pi radians, because days will cancel, and then I have 194 times 24. And that's going to be 4,656 radians per hour. So this is radians per hour. So that's the angular speed. Now for part C, they're asking for some other information. It says find the linear speed. Well, remember, linear speed is a different formula, and we want to make sure that we're finding this in miles per hour. So for linear speed, if I recall correctly, this is V equals S over T. So if I think about what I have here, S is arc length, this is R theta over T, but look at this, theta over T was omega, so this is R omega. So this theta over T bit is the omega here. Now the radius was given to us, it was 86 million miles, and again that was in the information up here, 86 million miles times omega, and our omega was pi over 4656 hours, and this is radians. And again, we're looking for miles per hour. Radians is just a way to help us keep track of things. It's not actually a unit of measure. So if we were looking for the exact value here, I could just say, oh, it's 86 million pi miles per 4656 hours. Now if you wanted, you could reduce that and that would be your exact answer. But let's go ahead and look for a decimal approximation. I'm taking 86 million times pi divided by 4656, and I end up with 58,027.69936 miles. So if they wanted us to round this to the nearest mile, the 6 is 5 or higher, so that would increase to an 8. So it would be 58,028 miles per hour. That would be our linear speed. So this was nice because they broke it down into nice steps for us to come up with the solution. But if they don't do that for you, you can still come up with those solutions and those answers. So again, it's important to realize that you can switch from one version of the formula to the other. For instance, up here we noticed that omega was theta over t, and that helped us out down here in this velocity formula. So as usual, if you have questions, please let me know. These are a little bit harder problems because you do need to read carefully for information, but if you have troubles, please let me know either during the lecture if you have questions or during the homework as well. Good luck!